Today we'll talk about several topics as shown on this next slide. The primary purpose of today's talk is to focus on the runoff aspects of any stormwater system, management system, and that's what the focus will be on. It derives the topics that we'll look at will be derived from a field called hydrology. What we'll go through is the first topic called a hydrologic cycle or hydrologic budget. You might see a problem or two in the morning session on this as a simple application of law of conservation of mass as applied to a water system like a catchment or reservoir. And then we'll talk about rainfall, which is the primary input to these hydrologic systems, is the primary reason why we have runoff. And in particular, we'll talk about design storms, which is what most engineers use in day-to-day design work. After we discuss rainfall, I'll talk a little bit about abstractions. That is essentially the component that's lost from rainfall, and that appears as runoff, and that's primarily what causes runoff. And I'll also discuss two main runoff methods that we traditionally use in design. For small watersheds, obviously, most people use what is called the rational method. We'll go over that. And for mid-sized catchments, the preferred method is the TR55 method, SCS, Soil Conservation Service. It's now called the NRCS, National Resource Council, Soil Council. And the unit hydrograph method, which I'll give you a brief overview of that. Nothing much, not much detail in that method, other than how it works. And so we'll wrap it up after that. And I've got some stuff in the appendices you can review on your own time, in particularly the hydrologic routing part of it, which I feel may be a little bit too advanced for the morning session. Here's a basic slide showing you what a hydrologic cycle is. The rainfall that falls on the surface either infiltrates or appears as surface runoff and in your streams and so on, and then takes off to your ocean eventually. And I've defined some key things here. For example, precipitation or rainfall is a discharge from the water from the atmosphere. We often use the word rainfall and precipitation interchangeably, but in general, precipitation is a more general term, which includes snow and hail and so on, or rainfall in other forms. Rainfall excess is what's after you subtract losses, and we'll discuss these losses briefly. Main one is the infiltration loss. That's the water that enters the groundwater system, and and that is basically what we call losses. If you subtract that from the rainfall, you get what is called rainfall excess. Then the remaining, obviously, that excess appears as runoff. The word runoff and rainfall excess are kind of synonymous. One refers to, as I said, the volume under a hydrograph. The other refers to the rainfall excess under a hydrograph. So I'll make this distinction through an example. Surface runoff is what appears, obviously, appears as in the nearest stream. Some commonly used units. These units might confuse you a little bit, so I thought I'll clarify this right away. By the way, I've got the chat box open, so if you have any questions along the way, please be free to send me one, and I'll try to answer as many as I can. The acre foot is a very unique volume in hydrology. It's 1 acre, 1 foot of water spread over 1 acre of the surface, which is a volumetric unit, and it's equivalent to 43,560 cubic feet. CFS, of course, most of you are familiar with that. That's a discharge or rate unit. And cubic is also a rate unit or a discharge unit in the SI system, meter cube per second. And of course, CFS days, kind of similar to acre foot. It's 1 CFS flowing for 1 day, which turns out to be 86,400 cubic feet of water, or simply put, 1.98 acre feet. The first unit, acre foot, and the last unit, CFS days, or we call it SFD, are commonly used in order to have more manageable numbers, because volumes, when we deal with runoff volumes, are usually huge numbers, like in cubic feet. We're talking about million cubic feet and so on. So we like to deal with numbers that are scaled down to something that we can easily handle. And that's why we use these units called acre foot and CFS days. I want to emphasize that acre foot and CFS days are volumetric units, whereas CFS and cubics are rate units. This distinction becomes very critical in the next part that I'll discuss here, called the water budget. Okay, we'll start with this word hydrologic budget. Essentially all it is a continuity equation or law of conservation of mass as applied to two systems we'll discuss here in our presentation. The first one I'll talk about is a hydrologic system, a watershed system or a catchment, and second I'll discuss the reservoir system. And I'll give you two examples here how to solve problems in either one of these. But the law of conservation of mass, or so-called equation of continuity, can be written in two forms. The first one is what I call a rate form. A rate of change of storage is equal to, which is ds over dt, is equal to inflows minus outflows. Or on the other hand, a volumetric form, which is shown here, where you multiply throughout by delta t, and you get essentially change in storage is the S2 minus S1 equals sum of inflows minus outflows. So that makes sense. Obviously, either form can be used readily adapted to a watershed system or a reservoir system. Keep in mind that S2 and S1, S2 is the end storage and S1 is what you started with in the beginning, S1. Delta T is a time increment or a time interval that we need to select, or it will be specified in the problem. Typically for a watershed system, we're looking at an annual time frame. Delta T is 1 year or 365 days. If we look at a reservoir system, typically it's 1 month. Average number of days in a month is 30.5 days is what you can assume. If not, if they give you a specific month, obviously the number of days will be known. Let's start with one example here for a watershed system. I kind of mixed up the units here a little bit so you can get a little better feel for how to tackle all these complicated units in hydrology, which is often causes a lot of headaches for a lot of students in this field. But nonetheless, we can work through that. Take a good conversion table with you. If not, I can email you one. But here we have, in this example, a 50 square mile watershed. The annual rainfall in the area is 60 inches per year. So note that data itself per year means it's on an annual basis. So in a sense, delta T that we talked about in the earlier slide, the time interval, it's fixed at 1 year. Assume runoff is 55% of annual rainfall, that is 45% losses. So the first thing we'll do here is to compute the volume of annual runoff from the watershed in acre feet. We want the runoff, remember, and later on I'll relate this to rainfall excess, but right now let's call it annual runoff. I want it in both acre feet and SFD. That's the first thing. And then we'll convert that to a rate unit. Of course, the 1 year is a fairly large time interval, so the second part really doesn't make a whole lot of sense in terms of its application because it's it's averaged over a long period of time. But let's look at the first one, the annual volume of runoff. That's in 1 year. Now, I wanted this answer in acre feet. So what you have to do is take the rainfall runoff depth, which is given right here. Remember, 0.55 is 55% appears as runoff, so it's 0.55 times the rainfall input, which is 60. So that'll be in inches. So you have to convert that to feet first. So divide by 12. So that gives you the total runoff depth in feet. And again, then you're going to multiply that with the area in acres. 50 times 640. So you'll get the total volume of runoff in acre feet, which is 88,000. Now that can be converted to cubic feet if you want. Notice how big the unit is. That's the reason why we often use acre foot as a volumetric unit in hydrology. Look at this number. It's pretty big. It's in the 10 to the power 6 cubic feet, million cubic feet, and so on. In SFD, it's also a reasonable magnitude that you can handle. Remember, the conversion to SFD requires the fact that one SFD is 1.98 acre feet. So if you took this in acre feet divided by 1.98, you'll get SFD. The reason I bring up SFD or CFS days is USGS uses this unit quite frequently. You might see that word, and a lot of times I've seen students who get totally confused when they see SFD and don't know what it is. I do have comment here. Audio is in and out. Are you all able to hear me clearly? Please let me know. Everybody else, somebody is having trouble, I think, getting the audio clarified. So hopefully, ASC can resolve that issue as we go along. Rate of runoff is basically take the volume of runoff, and I try to speak as loudly as possible. That's good. Some said they can hear me. Good. All right. If you can, let me know right away. Keep an eye on the chat box here. Our rate of runoff is essentially the volume of runoff divided by the time frame. In this case, we're talking about 1 year, which is 365 times 86,400 seconds. And so you took the whole volume, divide by that, you'll get a rate. So basically what this means, the way you interpret this rate is a flow of 121.55 CFS for 1 year would produce that volume of runoff. Okay. Now I'm going to do another example here. This time we're going to apply the same hydrologic budget equation to a reservoir system. Okay. And in this case, the time period I'm going to give you is 30 days because typically that's what we use, is a delta T of 30 days. Now in a reservoir system, it's slightly different from a watershed system in the sense that the stream flow from the catchment or from the watershed comes into the reservoir as runoff. That's what you just calculated earlier. And in this case, it's given as 5 meter cube per second. So it's an average runoff rate during that 30-day period. Water supply withdrawal, typically we give that in MGD. Reason being, water supply people like to use that unit in million gallons per day. That's what MGD stands for. That's a rate unit, remember. Q is also a rate unit. And the evaporation from the reservoir is given usually as a depth, in this case in centimeters or inches. In my example, it's centimeters. That also requires an average surface area of the reservoir in order to convert that to a volume. Remember, depth times area is always volume. In this case, that surface area will be given to you. I've kind of mixed up the units here. It won't be as bad on the exam, but generally I did this to illustrate how to, convert all these into a common unit. In this case, the reservoir surface area is 3.75 kilometers squared. Remember, kilometer squared is not a consistent unit in SI. Meter squared is. So you obviously want to convert that right away to square meters. And then, of course, if you can convert to square feet or whatever units you're going to go into. I'll solve this problem in all in SI units or in US units, and I'll do that on the next slide. Depending on that choice, you'll have to convert appropriately. The beginning storage is given in acre feet. So it's obvious that might be the driving force for selecting your units. Since this is a volumetric unit, acre feet, we'd like to eventually calculate our final storage also in acre feet. And let's go to the next slide, and I'll show you how to convert each of these into that common unit. So in this example, I've selected acre feet as my unit of computation. If the problem wants to compute it in cubic meters, then I suggest you redo this problem in SI units, okay? Maybe you want to go home and try that. Somebody is saying here, it says, you are sounding fine. Thank you. All right. I'm trying to speak as loud as possible, so hopefully everybody will be able to hear me very clearly. Here's a good example of a reservoir system, and I suggest most likely if you get a problem, it might be in this particular application right here. They'll give you a beginning storage. It's a simple mass balance, okay? The only thing you can goof up here is probably the units, so you have to be careful, watch out on the units. You have to know how to handle these units. Q typically, as I said, will give in cubic meters per second or CFS, but in this case, meter cube per second, so I multiply by number of seconds in 30 days because I'm converting it to volume. I'm multiplying by delta T. So that gives me so many cubic meters, which obviously I can easily convert to acre feet. So in this case, it's 10,508 acre feet. So you might want to look at your conversion table and see how to go from cubic meters to acre feet. Typically what I've done is gone to cubic feet first, and from cubic feet, it's easy to see the conversion to acre feet. Same thing with W, which is the watershed. This is the withdrawal from. So it's an outflow, okay? Q is the inflow. Outflow means basically a withdrawal. You're taking out some draft from the reservoir, so it's a loss. In this case, 136 million gallons per day is 136 10 to the power 6 gallons per day, and you want to convert that to cubic meters first, which is what I'm doing here. And from cubic meters, the conversion process to acre feet is same as what I did above for Q, and in this case, 12,521 acre feet. Evaporation, by the way, if they give you evaporation in centimeters, they also give a rainfall input directly. In my example, I don't have that. I do not have the rainfall input falling directly onto the reservoir surface. If it is, let's say, for example, 10 centimeters of rainfall occurs during that month, during that delta T or 30-day period. In that case, 10 centimeters of rainfall is input, evaporation 9.4. So what you can do is take off both, or one is an input, the other is a loss. So the net effect will be zero point 0.6 centimeters of inflow of input. So in that case, I would suggest you combine P and E together, rainfall and the evaporation together, and put it all into one calculation. Same thing with seepage. If they give it to you, it will be in centimeters. That's another loss, like evaporation from the reservoir system. So you can combine all those quantities that are specified as depth, like in centimeters, together. Okay. In this case, I don't have any of those. I just have evaporation. So I've got basically 9.4 centimeters of evaporation, which translates into 286 acre-feet of water. Uh, and therefore, once I've got all these volumetric units now, remember they're all volumetric units, because all of them some were rate units that I converted over into volumetric units. And finally, I do the mass balance. That's the final storage S2 is equal to the initial storage, which was 12,560 acre-feet. And of course, the inflow, that's the flow coming in from the stream directly into the reservoir system, was 10,508 acre-feet, which is right from here. And then, of course, subtract all the losses. In this case, you're withdrawing 12,521. That's the withdrawal from the reservoir for whatever reason, water supply, irrigation, and so on. By the way, that sometimes they use the word gross draft for that, so don't get thrown out by what they mean by draft. A draft is like a withdrawal from a reservoir system. Okay, in this case, it's 12,521, and there's the evaporation loss. If there is a seepage loss, include that too. If there's a rainfall directly input, it will goes on the left-hand side here in the plus column. So essentially what you're doing here is taking all the surpluses minus the withdrawals, and the net effect is, in this case, will come out to be 10,261 acre-feet of storage, which is less than what you started with. It's obviously a loss. Okay? Any questions so far? Let's see. Somebody asked me here, could you just do a cubic foot conversion from gallons? Uh, are you referring to, I'm assuming, let's see, which conversion are you referring to this one right here? Yes, you could do that. As I said, there are other ways to convert gallons per day. Yes, 7.48 gallons is 1 CFS. Yeah, that'll be fine. And then you can go to acre feet from that also. Yeah, there are other ways to do it. It's not just the only way, okay? Good question. I hope that's the thing you're seeking for, the answer. All right, moving on. I've set up a good problem for you to solve at your leisure. So please go through this whole problem. It'll take you through the process. Uh, the first one is very easy. This is basically the volume of water evaporated from a lake in acre feet per year. Let's just do that one, and you can send me the answer through the chat box just to get you see how the process works. What I want to hear is just the evaporation part of it. That's a loss, but I want it in acre feet per year. So what do you want to look at? You want to go back and look at basically evaporation, okay? In this case, the evaporation is 49 inches. So let's convert that to a loss in acre feet per year. Somebody asked me about finding some files. Oh, the conversion factors. Well, any unit conversion table should do that in any textbook, but I can send you one. Just send me an email note, all right? And I will be happy to share the one I have with me. But in general, you can get it from any textbook at the back of the book. Next is, it's really echoing and sounds horrible. I'm not sure what's causing that. I think my phone is all right. Let's do test here. Can you also, ASC, please check to make sure one of the participants is concerned about echo. Um, if it continues, please let me know. Here, reservoir storage computation. Yeah, what's the answer to the first one? Yes, I'm already getting some answers. Very good. Some are telling me that you can hear me clearly. Some are not sure. I don't know. Make sure everybody's okay with that. All right, 16,300. The answer is this part A. Very good. So let's move on to next one. You can do the rest. By the way, before you do attempt this problem, I just want to make sure you're aware of this note that I made here. It says in my part 2 of this question, I asked for essentially the inflow into the reservoir. That's the flow coming out of the watershed or catchment, the runoff. In that case, one of the things you might want to keep in mind is in my answer here, I've not adjusted for the reservoir area of 4,000 acres. What can happen sometimes is you have a 150 square mile watershed, but the reservoir, which is basically the lake behind the dam, can inundate a portion of that watershed, and therefore you might end up double counting that area for rainfall input. So what most people do is they subtract the area of that impoundment or the reservoir area from the watershed area, what we call make an adjustment before they do these calculations. So the runoff contribution must come directly from the area that's not inundated by the reservoir. Okay. So in my example, I didn't go through that because usually that's a small area compared to the watershed size. In this case, 150 square miles. Okay, let's see if everything sounds good. Somebody said, but doesn't the area of the reservoir still collect water during rainfall? As I said, no, don't do double count. Yes, if the rainfall comes directly, as you include that in your computation on the surface of the reservoir surface, that's an input directly into the reservoir. Do not count that as an input also into the catchment. So that's the reason why we make this adjustment in the area. Okay? That's a good question. Now, if you include the entire watershed area, you may not want to include that as an input into the reservoir directly. Okay? All right. So it's just to avoid double counting the input of rainfall. Remember, the input of rainfall into a reservoir comes directly as a contribution, whereas the input rainfall into a catchment undergoes a transformation because you have to abstract losses in the form of infiltration, not just evaporation, evapotranspiration, and so on. So the loss mechanisms are different. So a 10-inch rainfall on a watershed does not produce the same amount of runoff as a direct 10-inch of same rainfall into a reservoir surface system. There are no losses there except for evaporation. Okay? And somebody says, I hope that answers your question. The answer is yes, it does collect. That's precisely why we have to subtract this surface area of the reservoir from the catchment area. Okay. Next, you can go through the rest of the problem. They're fairly good problems to go through, so please do that. Let's move into another topic. These are kind of peripheral topics, and then I'll get into the main crux of what we're going to talk about today. This is a lot of times in many reservoirs, many streams, we do not have adequate water to supply a city to be able to withdraw enough water to meet the needs of, say, water supply, etc. Unless you're living along a big river like we are here in our city of Louisville, we have enough flow in Ohio that we don't have to worry about this. But in general, smaller communities do, and so they often have to provide what is called reservoir storage. There are two ways to assess how much storage they would need in order to meet those dry periods, so-called. One method is called the ripple method. It's a graphical method. I call it the mass curve analysis method. Most likely, the only way I see this problem on the exam is if they actually give you a graph, then it's easy to analyze it. If they don't, I'd suggest you do the analytical method, which is called the sequent peak method. I'll illustrate both these through an example in a minute here on the next few slides. Uh, I'm going to do this example in this case. Remember, the flow period they'll give you is a critical time period. They will not give you all the inflows, obviously. Typically, they use a 1-month time frame for that. So at a particular site here, it says the following mean monthly flows were measured in million gallons per month. So the unit is million gallons per month, volumetric. At a gauge in a river during a 13-month critical drought period. So I only selected a critical drought period of 13 months, determine the maximum storage required in million gallons to provide a constant draft of 35 mg. So what we're trying to do here is you got a flow system coming in as you're located on a longer stream. Notice in some months you have water more than what you demand or what your demand is. The demand is 35 mg per month. But there are periods right here during low flow periods where the inflow is much, much short or much, much less than what you're demanding. So how do we handle that scenario? Well, the only way to do is to smooth out these demand fluctuations. And therefore, the method to do that, or the way to do that, is called the mass curve analysis method. If they give you this graph, it will work fine, but I'm going to illustrate how this method works first, and then we can also move to the analytical method here. First, you develop what is called a cumulative inflow curve. The blue line shown right here is the cumulative inflows coming into the reservoir in million gallons per month. That's the unit. Uh, the pink line that I've shown here is the cumulative draft line. In this case, the cumulative draft was, the monthly draft was 35 million gallons. So if you accumulate that, you'll get a straight line, and you know the slope of that straight line, 35 million gallons per month. And what you have to do then is to basically take this pink curve and shift it so that it's tangent to the blue line of the cumulative inflow curve, and the tangent is at point P1 and P2. It will intersect that blue line at two critical points, and those are the ones that you need to make a note of. These 2 points labeled as P1 and P2 are essentially the points at which the reservoir is kind of full. It's come back recovered from the drought, and that's the reason why we focus on those 2 points. For example, P1 says if the reservoir is full at this point, and then the inflows start decreasing, but the demand continues to at 35 million gallons per month, then what's the maximum deficit we will experience, and that's the amount of storage you need to provide. So therefore, the difference between P1 and T1, that's called the trough, the lowest point, is the storage required. It's called sequent peak because you do have to identify the second point, second peak called P2, and I'll show you in a tabular form what this means. But at the moment, in the graphical type of depiction, P1 is the first tangent here, or the intersection of the first of this draft line curve with the curve, the inflow curve, and P2 is the second point of intersection. So you have to identify these 2 points in order to locate this trough, T1. In an analytical form, or in a tabular form, which is probably the preferred method, the same situation you have is the inflows are given, and the draft is also provided in the second column. Now what we have to do is determine the cumulative draft. That means basically all you do is accumulate all these inflows. In a sense, column 3, this column right here, is what I call cumulative mass curve in that graphics. The so-called the blue curve, that's how you develop the blue curve, is by plotting this as a function of the time in months. And then also the cumulative draft. This is 35 million gallons. You accumulate it like after 2 months it's 70, plus 35 is 105, etc. Take the difference, and that difference is basically what we call the deficit. In this case, I'm taking cumulative inflow minus cumulative outflow. A positive deficit means more inflow came in and less went out. So in this case, the peak P1 reflects that essentially the highest point where the flows were enough to supply the demand. But thereafter, when the inflows start decreasing, notice how the difference starts dropping. The trough will be the maximum critical deficit. Since you're taking cumulative inflow minus cumulative draft, this will come out negative. The most negative number will indicate that lowest point. That lowest point, by the way, is where you're trying to meet the demand at its maximum, where the inflows cannot meet it, and that's why you get basically a negative deficit, negative surplus. So that's called T1. And similarly, if you keep doing this, you can identify another peak called the sequent peak, P2. Then once again, the difference between P1 and T1 will be the critical storage. You have to take the max of either the difference between P1 and T1 or P2 and T2 if you can identify or locate another peak, P3. So in this case, 120 million gallons is the storage required because that's the difference between 79 minus 41. So be careful with this negative sign right here. There are 2 negatives that cancel out, and that makes that whole summation positive. Okay, so let's move on to the next topic. If you have any questions on this, please email me. I'll be happy to answer that. At the moment, I don't see anybody really questioning anything here. Somebody did ask, though, how did you get T2? This T2 right here, well, the record I've given you here is too short. I only gave you 13 months. In 13 months, I'm assuming the last peak right here, 104, is P3. It doesn't have to be, because if I gave you a few more months of record, It's possible that this 104 might become 110 and so on. The inflows will keep increasing, and that's when you locate P3. So P3 is the highest point again. Like we located, P1 was the highest here, P2 was the highest because after this, notice the flow started decreasing. So T2 is the lowest point after that flow starts dropping from peak P2, okay? All right. On the graph T2, well, if you go back to that graph, I did not show T2 is beyond this point right here, and that's for illustration purposes. I didn't want to, mess this figure up too much, but it is beyond P2, okay? If I had another 12 months of data, you'll have another curve situation like this. This curve will start going down again and then going up, so you'll get another trough further down after 13 months, okay? You have to look at the P3 before you can actually call it a T2, a trough 2. So that's why it's called sequent peak. You have to identify another peak, P3, that's greater than P2. Since you're accumulating the inflows, that will always be the case. So let's move on to the next topic here. We'll start with now the primary, we're going to mainly discuss today is the rainfall, which is as I said, is the primary input to our hydrologic system. That's what produces runoff. Now I'm going to primarily focus on what we use in design work called design rainfall. Where do we get this information from, and what does it take to define it? Before I do that, I just wanted to share with you some of you may not be familiar with this, particularly in other areas of practice, what a hydrograph is, and I've known a lot of people who forget what it is. It's basically a plot of rainfall, either in depth units, centimeters. By the way, the preferred unit is centimeters in SI, and US units is inches, or it's a plot of intensity, rainfall intensity, which is inches per hour, which is a rate unit versus time. That's called a hydrograph. Okay, so, but this information is measured usually by gauges in the US, and that information is often used to synthesize what we call design storms for design applications. So design storms are essentially standardized temporal rainfall distribution based on regionalized historical information, rainfall data. So they use the historical data as measured at several gauges to come up with this information. And I'll share with you how to get these design storms or where the source is from. Okay, the next thing we'll discuss, when it comes to rainfall or design rainfall, there are a couple of things that we need to pre-specify. Okay, you'll hear this in your problem statement itself. For example, frequency or return period. They'll say, what's the return period for your particular storm, for your design that you're going to select? And that's an independent choice depending on the system you design. I've included a table in the appendix. If I have time, I'll show you what it looks like. But typically, for example, if you're designing, say, a drainage system for a major highway, we're looking at a 50 to 100-year return period. There's a presumption in this that the return period of rainfall is also produce the same return period of runoff. That's strictly not true, but we go with that assumption since it is conservative. As a rule, the 100-year rainfall event does not necessarily produce a 100-year flood event or runoff event. That's because of the losses involved. Most studies have shown that it produces a 70 to 80-year return period of runoff. But we will not bother with that. We'll just assume the two return periods are the same. The next thing we have to specify is duration. You have to specify the duration of the rainfall. Typically, we take that equal to time of concentration of the catchment, like in the rational method, for example. The next thing, of course, the SCS, by the way, all specifies a 24-hour rainfall storm. They specify that storm duration, and that's what they want you to use. I will show you later. I will talk to you later about it when we get to that method. Intensity is the rainfall intensity is typically obtained from what we call regionalized rainfall data, which is from TP40 maps by the National Weather Service, or from intensity, duration, frequency curves. I will show you both what these look like, but that's where you get this information. Now remember, intensity and duration together, if you multiply the two, you get the design rainfall depth. If you ever need the total depth, the multiplication of these two gives you that information. Let me scroll down here because my chat box has gotten full. Let's see. Somebody said T2 is find storage correct. Well, P1 minus T1, that's the sequent peak thing. Somebody asked me if P2 T2 is greater than the other. Yes, that is true. That is the max storage. I agree with you. I'm sorry about this. Again, I didn't scroll down my chat box and I missed out some of these questions as they were coming along. Uh, Never mind, forgot the negative. Okay, the next is, does the design rainfall work for global climate change? That's a good question, and I wonder where that question is coming from. That's an interesting one. I have my own opinions on that, but let's leave it at that. I think all these design rainfall has to be probably revised in order to accommodate if there are some global climate changes, okay? That's going to obviously affect the whole definition of our regionalized data that we are using currently. Okay, I'll leave it at that. I know that's a big topic in itself. As far as you're concerned, if it impacts the design rainfall in your area, you should know how to accommodate that. That shouldn't be a major problem. But the question is how to quantify that effect. Anyway, I hope that answers this gentleman or lady's question about effect of climate change. The design rainfall depth, then there are two more aspects to rainfall: temporal distribution and spatial. Okay, temporal is time distribution. That's the hydrograph itself. There are a lot of design storms that fix this pattern. For example, SCS uses a 24-hour type 2 rainfall. I'll show you what it looks like. The only time that's important for you is if you're using a unit hydrograph type of methodology to determine the peak flow. I'm going to de-emphasize that in the morning session because I don't believe they will ask you to do something like that, and therefore this is not an issue at the moment. Spatial, this is an issue if you're dealing with large watersheds, greater than maybe 100 square miles. Typically, the average rainfall depth has to be decreased by a certain factor, and so I'm not going to cover that here because my discussion here is primarily focusing on methods that are suitable for small watersheds or small catchments. Here is the information for regionalized intensity, duration, frequency equations. That's one source of getting IDF intensity, design rainfall intensity for the U.S. This is a very important map. Please take this with you if you can for the exam because in the absence of an IDF equation, if they don't give it to you, this is the only source you have. This map shows you 7 regions in the U.S. and it's supported by a table on the next slide. And use these tables and these equations that are given for each of those areas. For example, we are in area 3 here, and say I want to design 100 years design rainfall depth or design storm, then the rainfall intensity duration intensity is obtained by this equation. I is equal to 7370 or T plus 31. Please make sure you watch the units. Those are very important. Unfortunately, the units of intensity is in millimeters per hour, not in inches per hour. So you'll have to convert it after you calculate the quantity in millimeters per hour. And then time is, of course, in minutes, not in hours. So make sure the units, you respect these units because these are empirical equations. Okay? I'll show you one of these equations later on how I'll use it. But if you have what I call intensity, duration, frequency curves for your area, which most major cities in the U.S. do, then use those accordingly. These are for Louisville, what I've shown here. Notice the vertical axis, you have the rainfall intensity in inches per hour, or the horizontal axis, you have the time in minutes, TC. It goes up to 120 minutes only, because beyond that, these curves get very flat, and they recommend just using an equation to get the rainfall intensity. But for the kind of design work I'm talking about here, or design methods I'm going to talk about here, the SCS and the rational method, we're talking about small watersheds, less than 50 square miles definitely, and therefore the time of concentrations are not going to be more than 2 hours. And that's the reason why our duration here, these curves are limited to 120, or maybe 180 at the most, 180 minutes. Now, the top curve is for a 100-year event. The bottom curve is for a 2-year event. In this case, for Louisville, 60-minute duration storm will give you an intensity of 2.8 inches per hour, which can be converted to a depth. Since 60 minutes is 1 hour, that also represents 2.8 inches of rainfall depth for the design storm. Okay. Now, what I've done is set up a small example for you to show you the use of that equations as well as the IDF curves. In this case, I just chose Louisville to illustrate that point. We are in region 3, as I said. Here's the rainfall intensity. Uh, I'm going to compute basically for a time duration or duration of 60 minutes rainfall. And in this case, the rainfall intensity comes out to be in millimeters per hour, 90.989. That converted to inches per hour is 3.2 inches per hour. And the rainfall depth is 3.2 inches. Notice that there is a difference. Uh, Somebody asked a question here. Will the exam question let you know what area you'll be making calculations for? Some states are defined by 2 or more regions. Yes, they should. Or they'll give you the IDF curve, one or the other, okay? So, I mean, you have to be able to locate which region you are. That's the reason I shared that map with you, depending on where your location is. All right, in this case, for example, region 3, if you go back to that map, I'm assuming that's what you're referring to is this region here. But region 3 includes a lot of states, and some states are kind of split too. So if you're going to use this map, you have to obviously know where you are and use the equations accordingly. It's very hard to find these equations. So for some reason, many textbooks don't do it anymore. So anyway, there's a difference between locally developed IDF curves versus regional. Now, I mean, some of your review manuals might have a different equation table, but it doesn't matter which one you use, they all give about the same. In this case, obviously there's a difference when I used the IDF curves for Louisville versus the equation. Obviously, it's better to use the locally developed IDF curves if you have them available. I've set up a small problem for you. I think we may be running short on time, so I'm going to let you work on your own time here. But essentially, there are 3 parts to this question. First, I want you to calculate the 100-year 60-minute rainfall for Chicago. These curves are for Chicago, Illinois. Notice these curves are sloped slightly different from the ones for Louisville, uh, and that's the way they set them up. Basically, they still slope downward, but the 100-year curve is on top, just like the Louisville, and 2-year at the bottom. The time of duration of the storm is given on the horizontal axis, and on the vertical axis is intensity. In this case, it happens to be in inches per hour, so you should be good to go. I also gave you here in question number 2 to compare that with the IDF equation for Chicago. Uh, they happen to be in the same region as Louisville. So please work on that and see what you come up with. The next thing, as I said, when it comes to a actual design of any sewer system or storm system, stormwater system, management system, we need runoff. Runoff is rainfall excess. So essentially, we have to find a way to convert the rainfall to runoff. There are several ways to do this. By the way, that's called effective rainfall or rainfall excess. The subscript that we often, or the symbol that we often use is capital P with the subscript E. The reason we switched to this as opposed to capital Q, which SCS continues to use in their terminology, is direct runoff. They use the same symbol for direct runoff because we typically use capital Q for discharge in hydraulics as well as in hydrology. So in order to avoid that confusion, many of us have switched to this symbol. Capital P is cumulative rainfall. Capital P with the subscript E is cumulative rainfall excess. Keep in mind the alphabets with capitals, alphabets are all cumulative values. And when I get to the SCS method, you will see that's very, very important. You recognize that. They do not deal with incremental rainfall. They only deal with cumulative. Uh, Again, abstractions. What are the abstractions from that rainfall to produce rainfall excess? Well, the first two, the last two here called depression storage and interception, they are the ones that actually happen in the beginning of the storm. Depression storage is the amount of rainfall that takes to basically wet the surface. If it's an impervious area, some water is required to wet it before you see runoff. And interception is typically by vegetation. If there's a lot of vegetation or trees, they intercept some water. The way we handle these two is through the concept of what we call initial loss. And I'll show you when I get to those two methods, the rational method as well as the SCS, where in that method do they get rid of this or recognize the effect of these two. But the main loss procedure is what we call infiltration. This is essentially the main loss that continues through the storm event. Depression, storage, interception happen in the early stages. Then they stop. But infiltration continues. That's the water continues to infiltrate the soil, even if it's saturated, by the way. So, the, so let's talk more about that method uh, in our discussion here because that's the most important one. There are several ways to recognize infiltration or model infiltration, if you want to call it that. The most popular one are the infiltration index using indices like a phi index, which will probably be given in the problem, by the way. They now ask you to calculate this because it's a fairly complicated procedure to do that. But it will be specified in inches per hour or in centimeters per hour. The rational method, of course, uses what's called the runoff coefficient C, which, by the way, is like an index, infiltration index. It turns out to be the ratio of rainfall excess to runoff to rainfall, or runoff to rainfall. SCS method uses what's called the curve number method. That's again an index they use in order to make that conversion from rainfall to rainfall excess. And finally, some states still use what is called the infiltration capacity curves. I will not cover that in our discussion here. It's a fairly complicated procedure, but if some of you may or may not have heard of this called the Horton's method, you might want to review this in any hydrology textbook. It's basically an exponential type of curve. So anyway, that's what they use in some states, but the most popular ones are the first three. And I'm going to give you a set of a small example to show you how a phi index works, because if you see a problem in the morning session, this might be one way they might ask you to compute the rainfall excess in a storm. I've taken the liberty here to include a direct runoff hydrograph also because I want to show you how to calculate the volume of direct runoff under a hydrograph. In this case, this rainfall produced that direct runoff hydrograph, so the two volumes must match up. Usually they don't, but it just happens that just to make a point that the volume of rainfall excess must be equal to direct runoff under the hydrograph. Thus, mass balance must be satisfied in this situation. But anyway, that's not the main point I'm trying to make here. I'm going to show you how to use the phi index. So here we have a direct runoff from a 7 square mile watershed. The uniform loss rate is 0.5 inches per hour, and calculate the volume of direct runoff in inches. So if you look at the hydrograph here, it's given in inches per hour, so the unit must match up. The time interval is every half an hour. So please make a note of that. This 1, 2, 3 that I've shown you are not time in hours, but they are time periods. So in this case, time period is every half hour. So the first half hour, for example, the intensity was 2.7 inches, and the phi index says you abstract at 0.5 inches per hour rate. I'm going to assume initially that I is greater than phi at all in all time intervals. If that's not the case, then make sure you recognize that phi will be equal to I in those intervals. That means, for instance, if the rainfall intensity in the first time period was less than 0.5 inches per hour, like say zero point 0.2, then there won't be any rainfall excess in that time period because the infiltration rate will be equal to I. That means all the rainfall that is falling is going to infiltrate at that rate. And therefore, there won't be any rainfall excess in the first time period. So it can happen, usually it happens at the beginning or in the end of a time interval, because that's when the rainfall intensity drops and can drop below the phi index value. But in this example, I've set phi index lower than all the I values just to show you, not to confuse things. So on the next slide, I'll show you how to calculate rainfall excess. I'll also show you how to calculate rainfall direct runoff volume from this hydrograph, those two computations. The first one is shown in the first step, rainfall excess computation. There is the rainfall 2.7 minus the phi index. So these are both in inches per hour. So therefore you get 2.2 inches per hour times half an hour is the time interval. And then do the same thing for the next time period and the third time period, and add them all up, you'll get 4.8 inches. Please do try this out after you get home immediately because it's easy to forget. Somebody asked me, where do you use 60 minutes? Are you referring to, let me see, the IDF curves, or which one is 60 minutes? I'm not sure that question. Somebody raised a question. I'm kind of lost track of the sequence here. So will the exam let you know what area? That I've already answered, but this one I'm not sure. Which duration are you referring to? Slide 20? Okay, let's go to slide 20. Somebody asked me about 60 minutes. That's the duration of the storm that I picked for this example, okay? 60 minutes. It's a 1-hour design storm. If you use 30 minutes, then you use 30 accordingly. Does that answer your question? Yeah. Why did you use 60 minutes? Because I'm figuring out a 60-minute duration storm. All right? Okay. I hope that answered your question. But let's go back to that fee index computation, volume of rainfall excess computation. Now, I'll also show you volume of direct runoff because later on, I have another question for you in terms of unit hydrograph where I expect you to calculate the volume under direct runoff hydrograph. So please try to understand how this can be done very quickly and easily. If the direct runoff hydrograph is given, typically they'll give you in CFS the ordinates. In my example, that's what I gave you on the previous slide. If you look at the units here, Q is in CFS. These are instantaneous discharge values of the direct runoff hydrograph. That's what we call a hydrograph. It's a plot of Q in CFS versus time in hours. Okay, but remember the time interval is every half an hour. That becomes critical too. So what I'll do is first I'll sum all these ordinates, instantaneous ordinates, together because the time interval is constant. So I sum all the ordinates and multiply by half an hour, which is the time interval. That gives me a volumetric unit under the hydrograph in CFS per hours. Now you remember this unit I told you about SFD, I've mentioned that unit, but I did not mention a CFSR. That's one CFS flowing for 1 hour, by the way. Therefore, using that 1 hour of 3,600 seconds, I can convert that to cubic feet. So it is a volumetric unit in cubic feet now. That's the volume of direct runoff under the hydrograph. Now, from this point onwards, I can convert this into depth in inches if you know what. Basically, the binding variable is the drainage area. Somebody gave me the size of the watershed. I will then calculate the watershed size in square feet. From square miles, I'll convert it into square feet. And if you divide this volume of runoff from the drainage area divided by the drainage area in square feet, you'll get the depth in feet, which you then convert to inches. In this case, it turns out my runoff volume is also 4.8 inches, which, by the way, is the main challenge in hydrology, is to ensure the one volume of rainfall excess that you calculate under a hydrograph also produces the same amount of runoff, rainfall excess, or basically runoff volume under the hydrograph. Uh, if the two are equal, that means you're okay. In this case, rainfall excess is equal to the direct runoff. But the main reason I put this slide in here is to illustrate two parts to this problem. One is to calculate rainfall excess from a hydrograph. In this case, I was using the fee index, but you could use any other loss index. And then the other is how to calculate it from direct runoff hydrograph. Okay. By the way, the symbol we use for runoff volume under hydrograph is RD. Unlike what we used here was, if you recall, was PE, capital PE. So slightly different. The two products are different. Okay. Now let's start with the primary focus of our discussion today is what are the design runoff methods. Remember, up to this point, we talked about rainfall. We talked a little bit about how to convert that rainfall to runoff, but the primary thing is we know how to select a design storm or design rainfall. Now, all these methods that we're going to talk about here, two methods, mainly the rational method and the SCS method, use this information. Let me scroll down my chat box because I've got a lot of other questions coming up here. I sometimes lose track of this. Can you say how you calculated PE again? Somebody's asking about, let me review that again. He wants to know how you calculated this PE, rainfall excess. Well, what you do is you take your rainfall that's given, the rainfall rate 2.7 in the first time period, inches per hour. You subtract the fee, the loss rate fee index, we call it the fee index, of 0.5 inches per hour, okay? So that difference gives you rainfall excess rate and multiply by time. So inches per hour times delta T should give you inches, okay? Do the same thing for each time period because your hydrograph, remember, has 3 time periods. First time period, second, and third. So do this, repeat that process for all 3 time periods and add them up. That's how I get that rainfall excess. Somebody asked me, the next question is, where is the equation? I don't know what he's referring to here. There's no equation, it's just that you have to mathematically calculate that. I don't know what he's referring to there, but anyway, the next is for PE. There's no equation, not in this method. This is just a simple computation, like a trapezoidal rule. Do you know how to calculate area under a rectangle? That type of an approach. That's what we're doing here. It's not that hard to do that part. Next is 195. What is this question? 195,148. I'm not sure this gentleman what question he's asking there. Why is the 2.7 as well as the zero point 0.5 loss rate both divided by 2? Uh, isn't the 2.7 already half an hour? No, the 2.7 is in inches per hour. If it's specified as a half an hour, then okay, let me go back to that. The rainfall intensity that's given here is 2.7 inches. That's on an hourly basis, not a half hour basis, okay? If somebody gave it to us on a half an hour basis, then the intensity will be different. It will be twice that amount. So the bottom line is when you multiply that with delta T in half an hour here, you should get the same rainfall excess amount of 2.2 inches. It doesn't matter how you represent the rainfall intensity. The bottom line is if you take the difference, the phi index should have the same units. That's it. So if this was in 2.7 inches every half hour, then you should have this also as zero point 0.5 inches every half hour. Is that clear? So the units must match up. Okay? So don't let that half an hour time interval throw you off. If the rainfall index is in inches per hour, which is typically the unit we use, then the phi index must also be given in the same units. All right, let's see if there is any other questions because we got a lot of material to cover here. I don't want to get stuck with everything here. We'll be given the phi index, yes. Somebody asked me, will you be given the phi index? Yes. I said that it's hard to derive it, so they should give it to you. I is 0.25. I'm not sure what this is. Shouldn't I be equal to 0.25? I'm not sure where that question is coming from. If your infiltration index is greater than your rainfall intensity, you don't introduce negative rainfall. That's what I just said. If I rainfall intensity is less than the phi index, use the phi index equal to I. Okay? It does not produce negative number if you do that. So what this question is, I think I already mentioned that. If, for example, in the first time interval, the rainfall intensity is less than the phi index, like say zero point 0.4, then don't take zero point 0.4 minus zero point 0.5 because that'll give you a negative intensity. No. What you do is you just assume that this first time period, the loss rate or the rainfall excess rate is 0 because the loss rate is equal to the rainfall intensity rate. So all rainfall will go as loss. Okay? I meant phi, yeah. So I'm not sure about this question either, the next one. If you're interested, that's one I just answered, okay? If you have any questions, please email me. I'll be happy to elaborate that further. All right, going back to where we were, the first method, we're going to discuss the rational method. This is ideal for small catchments, less than 100 acres. It's used widely in urban stormwater management design. And basically, the method is designed to give you a peak flow so you can size a stormwater system to handle it. It requires the following things. A runoff coefficient C. I'll show you on the next slide. It also requires a maximum rainfall intensity in inches per hour. That's what we call the design storm. Typically, that's based on a duration equal to the time of concentration of the watershed, so it'll require that. And finally, the catchment area has to be in acres or in square kilometers. So I'll show you that formula, what it looks like. In US units, it's C.I.A. And the reason it's called the rational method is because if I is in inches per hour and area is in acres, you magically get CFS because one CFS is equal to 1 inch per hour times 1 acre. C is dimensionless, by the way. This C is the runoff coefficient. It is essentially the ratio of rainfall excess to runoff, to rainfall. So that means direct runoff to total rainfall. But I'll show you in a table how to get that C from. This is in SI units, this formula. I suggest you use it, the one of these formulas, particularly the first one, where the rainfall intensity is typically in millimeters per hour and area is in square kilometers. Please make sure you respect the units either way. This area must be in acres, not in square miles, for the rational method in the U.S. method. Okay. Um, so moving on, here's the table for where you can get the rational method C from, the coefficient runoff coefficient. Notice the function of land use in the first column here, and in the first row on top, it's also a function of return period. What they found is the runoff coefficient C increases. That means there's more runoff as the storm intensity increases. There's a 100-year storm, for example, will produce more runoff than, say, a 5-year storm. And that's why the runoff coefficient for the same type of surface, in this case an asphaltic surface, is higher for a 100-year event than for a 5-year event. Asphalt surface right here in the first column. Anyway, a lot of these are shown for different types of land uses. So please consult one of these tables. I'll show you through an example how to handle this runoff coefficient C for different areas when you combine them. The next thing is the time of concentration. Typically, the definition of TC is the total travel time from the hydrologically remotest point in a catchment to the outlet. Okay, so in this case, I've shown these squigglies, by the way, that I've shown is typically overland flow time, and the travel time in a particular pipe or ditch segment will be shown in a solid line like this, like in this case T2. T1 is the high maximum overland flow time, either this path or this path, and that is the time to this particular inlet point right here. And when you come down to this inlet point, you have to compare all possible paths of flow to that point. In this case, it will be either T1 plus T2 or T3 and T4 taken individually. So in that case, TC at that point is the max of those three travel times. So basically in the rational method, depending on which point of application you are or which point in the system you are, you'll have to redefine the time of concentration at every point. And that's because we're going to do a computation of peak flow every inlet point as we go from upstream to downstream. We'll do that. I'll show you that in an example also. In this case, I've set up a small problem, nothing big. There are two areas, like area A1 and area B, draining to a common manhole. And what I'm going to ask you to do here is to basically determine the peak flow for a return period of 25 years. And somebody is asked me a question here again. Let me see if I can answer that. 0.25 would have been correct if placed outside the parentheses. Are you referring to going back to the fee index? Well, I guess I can't do that at the moment, but I think that'll work. Okay. I will come back to that. Or can you send me by email? I'll be happy to answer that inquiry. All right. In this case, the peak flow QP. Let's calculate the QP for a 25 return period. The size of the circular, I'm going to size a pipe to handle that peak flow. The Manning's N is 0.025. The slope is given for the pipe. Basically, I'll tell you where to get the slope from in a minute. And then the IDF equation is specified in this problem. It's for Florida, Tallahassee, Florida, and here's the equation. So all the pieces of information that you need are given here. By the way, the slope of 0.005 that I'm referring to here will be the slope that you're going to put this pipe on. Usually that's determined from the invert elevations of these two manholes separated by some distance L. So let's see how to solve this problem. First, there are two areas draining to manhole, the upstream manhole. We're going to determine what is called a composite C first. And that is C1A1 plus C2A2 divided by total area will give you a composite C value. And that is essentially the way you determine the average C value for these two areas A and B that are draining to this manhole point right here. If there are three areas, then use all the three areas. I've kind of given you in this insert the formula to use, but in general what we're doing is doing a weighted average of the runoff coefficient based on the areas. The time of concentration, as I said, is the maximum of the travel time between those 2 points. In this case, max of 20 or 60. Remember, the TC for area A was 20 and area B was 60, so I took the maximum of 60 minutes. The 25-year rainfall intensity is what I'll need for my determining the peak flow, and that is obtained from the IDF equation for Tallahassee, Florida, 3.5 inches per hour. As I said, the answer will come out in millimeters per hour. Make sure you convert it into inches per hour. Finally, the peak flow itself is 409.5 CFS because that's equal to C, which is 0.39 from here. I is the rainfall intensity, which I just determined from the IDF equation of 3.5 inches per hour, and times the area. Be careful with this area. That has to be a total area of the two area A and B combined because those two areas are draining to the inlet of 300 acres. So that'll give you 409.5 CFS, and finally is to get the pipe diameter. I've taken the liberty of using this equation, which, by the way, mathematically is derived from the Manning's formula, which I cannot get into at this point. Maybe later on I'll show you what the Manning's formula looks like. But this assumes full pipe flow. That means the flow area in the pipe is pi d squared over 4, and therefore the hydraulic radius of the pipe is also 1/4 the pipe diameter. You can easily manipulate that equation to get this. Also, I'm using US units. If you recall, the Manning's formula is 1.49 in US units. It's 1.0. The coefficient is 1.0 in SI. I will refer to that when I get to the Manning's formula a little later on in the discussion. At the moment, please use this equation as is for calculating the pipe diameter. Obviously, the unit will come out in feet, consistent unit. Q will be in CFS, for example. In that case, convert feet into inches, and that's what I'm doing here. The answer comes out in feet. Okay? All right. Let me see if I have any questions I can take at this point. Uh, yes, no, that was in response to, I'm not sure about that. As I said, to that particular question about the fee index, please give me an email. Again, somebody's having trouble with the voice. I hope most of you are not experiencing that. Huh? Okay. Maybe I'm trying to adjust my mic here, make sure we're clear enough. We have to be concerned with choosing a method, rational method, or curve number, rational threshold for, yes. Somebody's asked me if you're asked to choose a method, then yes, the answer is if it's less than 100 acres, I won't even go 200, then I'd go the rational method. Beyond that, yes, the SCS is the preferred method, okay, which is what I'll do next. All right, are there any other questions? I don't see any, so we'll proceed. I've set up a problem for you that you can work through for the rational method here. It is a little more complicated than you might like, and it's on the previous slide, I'm sorry, on the graphics of it. I just set up this as a whole problem just to show you how the rational method is in general used, but you don't have to solve the whole problem. I'm only asking you to solve for this area 3 right here, and that drains to a point E, the runoff from there, and then you're supposed to size this pipe EB so it can handle the runoff from point E to point B. For those who want to get challenged a little more, you can solve the whole problem, for which I've given you the answer on that slide. But in this case, there's area 1, 2, and 4, 5 all connected. If you're going to only do the E to B path, key thing here is basically all you are interested in is the time of concentration of area 3, which is given right in this table. That area is 4 acres in size. It has a runoff coefficient of 0.6, so there's no multiple areas involved at that inlet. And the inlet time or time of concentration is 10 minutes. This is based, when they refer to as inlet time, direct to the inlet, they already computed the time of concentration for you. And typically for small areas like this, area 3, that will be overland flow time mainly. Of course, then, for example, once you come to point B, then then defining time of concentration gets a little more complicated. The reason I say that is for inlet B, for instance, the time of concentration will be based upon 1, 2, 4, 5, and 3. All these areas get involved because they all drain to that common point. So again, the rule is simple. You're going to pick the maximum travel time along all the possible paths of runoff to that point B. In this case, it will be from this path, from this manhole, through this pipe to that manhole, or directly from area 4 or 5 draining to that point, shown by these squiggly arrows right here, or from area 3, but area 3 comes through the pipe, so you'll have to include the travel time in the pipe too. So you compare all those travel times and then take the max for the time of concentration parameter at point B, at the inlet manhole point B. Also remember there's more area draining to at point B. You have to combine all the areas 1, 2, 3, and 4, and 5. And also they have to composite the C values for all those 5 areas. And therefore the total runoff volume or the peak flow will obviously be greater than, say for example, manhole A, which is expected, because as you go downstream, the peak flow is going to increase. Okay, so if you want to solve the whole problem, that's fine, but I've generally asked in this case only for that area 3. So please work this problem out. Now here's the whole table showing you the entire problem, which is a typical urban stormwater drainage system problem, which I've kept it fairly simple. So if you can work through, keep in mind that after you select your pipe, which is right here in column 9, what we do is we, sometimes that might differ from the available pipe sizes commercially. So we modify that a little bit. For example, for pipe AB, instead of 1.94 feet as you get from that formula, we use a 2-foot or 24-inch pipe. In that case, after you do that, then you calculate the flow velocity. The reason you need this velocity is in column 11 is to calculate the travel time in that pipe. Remember, eventually we have to determine time of concentration downstream, so we have to include the travel time in each pipe. And that travel time, by the way, is shown in this column 6. Okay? So please work through that. Let's go over the T of it 5 method now, since we might be short of time otherwise. So let's see if there are any questions before I start this discussion. Uh, somebody is saying that audio issue started from slide 28, could not hear anything. I'm sorry about that. She wants me to repeat starting slide 28. Now that'll be kind of difficult to do. Let's see, we are on which slide right now? We are on slide 35. Somebody's saying slide 28. Uh, that puts me down here to the rational method. Well, I probably might end up losing a lot of time, so for the interest of the other participants, I apologize. But anyway, this is the rational method. Uh, yeah, for other people, the audio is fine. I'm sorry about that, so I need to go ahead with my presentation. So for the person who could not hear me after slide 28, please, I'll be happy to answer it through email, any questions you may have. Okay. Also, there will be a recording, as somebody is pointing out, so you can listen to that. Please request a recording of this particular session, and you can catch up on that too. Thank you for reminding me about that. Anyway, the next thing we'll talk about is the TR55 method. This is a very important method, so I'm going to go through the basic steps involved. As I said, this method involves a design rainfall of 24 hours. That's what they normally recommend. And what you need from that is a cumulative rainfall in inches for a given return period of frequency. So once you say you selected a 100-year design storm or design rainfall event, you go to this figure, a TP40 map like this, or most likely they'll give it to you in the question itself. If I'm, for example, in Louisville, I'm between this curve right here, which is basically, if you follow that curve down here, it's about 6 inches curve, and then as further south you go, that'll be an 8-inch curve. So we're around between 6 and 8. So I would say roughly, I'm sorry, the 8-inch, we're between 6 and 7. That's a 7-inch curve right there. So we're around 6.5 inches. Typically, I would prefer to get this from an IDF equation if they give it to you. Remember, IDF gives you the intensity, doesn't give you the depth, but you can always multiply by duration to get the total depth. But most likely, they'll give you this rainfall information. If not, I suggest you download TR55 manual. It's a PDF document from the SCS website. You can Google it very easily. And they have all this information in their appendices, depending on which region you're located. They're much clearer figures than what I'm showing you here in my presentation. Most of the coverage is on the eastern part shown here, but they also have figures for the western part of the United States. So please download if you can, and that'll be a very useful document to take with you. The SCS curve number is the next thing that we'll need in order to calculate runoff or rainfall excess for this method, and that can be obtained from a table like this, like the rational method. We have a similar curve number table method here. Notice the land use is a function of land use. There are several types of land uses here, including urban type of land use. And on the top row here, there's what we call a hydrologic soil group. They use 4 of those, the SCS. A is a very sandy soil. They drain well. And B is kind of a in between silt and clay. Uh, Finally, D is a very impervious type of soil, like a clay, stiff clay soil. And you'll notice the runoff coefficient increases for a given particular land use as you go from hydrologic soil group A to D. The runoff coefficient increases, the curve number increases, indicating that there'll be more runoff, obviously, and less infiltration. So a higher curve number, more the runoff. You also have, for example, I will talk about this. There's a footnote here that becomes very important. If you're going to use the curve number shown in this table, for example, let's say a one-third acre lot residential area, they assume 30% is impervious and 70%, the remaining 70% is open space in good hydrologic condition automatically. And therefore, what you see a curve number of 81 here is composited by taking 74 curve number for open space in good hydrologic condition multiplied by zero point 0.7 plus the remaining 30% is pervious, is impervious, that's a curve number of 98. So you'll end up with 81. If you if the problem says that the open space is not in good condition but fair condition, please do not use these curve numbers from this table. You have to do your own composite, okay, on your own. Or if the one-third acre lot has more perviousness or imperviousness than indicated here, you'll have to composite the curve number yourself too again. So my recommendation to overall is be careful when you select a curve number here that's based on any kind of compositing. On the other hand, for if you go use, for example, pasture or cultivated land, those curve numbers, they're obviously based upon experimental work, so there's no compositing involved there, so you should be okay with those curve numbers. I'll show you an example how to use that in a minute. And finally, the equation that they use for determining rainfall excess is this equation. I also want to make a note here that since they use the symbol capital Q, and remember, if you recall, I said we like to switch to PE. Those two are the same. Also, I suggest not to use this graph, although I'll show you how to use them. That's the reason is, in using this graph, you're committed to this rainfall runoff, the runoff equation, which is given here in the insert, and that assumes the initial abstraction IA as 0.2s. And that may not be always the case. If it is 0.1s, for example, you cannot use this graph at all. So be careful in using this figure if that condition is not met. I suggest always use this equation. And let me explain what this equation is. The capital P stands for cumulative rainfall. That's the design rainfall, in this case the 24-hour rainfall. The IA is they call it the initial abstraction. It's like an initial loss, which is in this case equal to 0.2s. They assume it's equal to 20% of what they call the sorptivity parameter, which is that capital S. And that S is obtained is a function of curve number, and it's equal to 1000 over Cn minus 10. Please be careful when you calculate this quantity right here, because a lot of times in a hurry you forget about this parentheses right here. So what you end up doing is taking 1000 minus 10 divided by curve number. No, you divide the 1000 first by curve number, then subtract 10. All right, so be careful with that calculation a little bit. Also, I want to emphasize all the SCS always uses everything is cumulative. Capital Q, capital P, they're all cumulative values. The initial abstraction also is cumulative. That's the total abstraction, total loss, not just incremental. And furthermore, I suggest you use this in SCS, in SI US units, because that's what this method was based upon. So if a problem gives you in centimeters, I recommend you convert that to inches before you use this method. So total rainfall excess must be in inches, rainfall must be in inches, total rainfall, and everything else will work out fine. Okay, so that gives you, this equation gives the volume of direct runoff, what we call rainfall excess in inches. I'll give you a small example right away to show you how this computation can be accomplished. In this case, I've intentionally specified my own design storm. I'm not using the SCS design storm, but in general, that's what you should be doing. This just illustrates a different type of an application. Rainfall, rain falls on a 5.05 square miles watershed. Immediately you must recognize that that area, uh, particularly if you use the rational method, should be in acres. So I also gave it to you what it is in acres. It's an urban catchment with a rainfall intensity of 0.85 inches per hour for a duration of 3 hours. So the reason I give you that information is to calculate the total rainfall, cumulative rainfall. So it'll be a good practice for you right now to calculate total rainfall from a design storm that's given like this. The soil is classified as a hydrologic soil group C, and that particular, this catchment is broken up into the following two types of land uses. A business district, 20%, and 80% residential. Within the business district, 85% is impervious, and obviously 15% is pervious. It's very important that you note what that pervious area is going to be. If it's not specified in the problem, the pervious area, you have to assume it's in good hydrologic condition to use that table that I just referred to for the curve number. Same thing with this 80% residential district. 1/3 acre lots, that's what you're going to develop with 30% imperviousness. That means the remaining 70% is assumed automatically and as in good hydrologic condition. That doesn't have to be the case though. So watch out for the undeveloped situation, because later on I'll show you another example where I do account for the fact that the undeveloped area may not be the one that is assumed in that curve number table. In this case, let's do the compositing, SCS curve number first. By the way, the goal is to determine the volume of direct runoff. That's what I'm going to illustrate to you using this SCS method. In this case, the first thing we had to do is to composite the curve number for the entire area. And the business district curve number first, it was 85% impervious, so 0.85 times 98. The remaining 15% is pervious in good hydrologic condition. From that slide on the curve number table, that's a curve number of 74. So total composited business curve number for the business area is 94. I do the same thing for residential area. It's 1/3 acre lots that has 30% impervious, curve number 98. Notice here, instead of taking the curve number directly from the table, I could have. I'm doing the composite myself to illustrate to you that I get the same curve number of 81 as given in that table. So if we go back to the table briefly, I'm referring to this table. There's the curve number 81 for a residential area, 1/3 acre lot size with 30% impervious. You get the same curve number. Okay, so basically 81 comes, I composited, you could have gotten it from the table. And then finally you have to composite all of those curve numbers together, simply because the catchment has both the business district land use as well as residential use. So assuming there's nothing else, no other kind of land use, for example, they might say another 10% is reserved as open space or something. So you got to factor that in if that is the case. In this situation, I'm assuming that these are the only two types of land uses. One is 20%, the other is 80%. You composite these curve numbers again, you get an overall composite curve number of 83.6. Now, therefore, I'm going to use that curve number now to calculate a couple of things for you. My goal, remember, is to calculate the direct runoff volume in inches. In order to get there, we first have to know what the total rainfall depth is as required by the SCS method. In this case, total rainfall P. It's 0.85 inches per hour times 3, so you get 2.55 inches. Remember, I specified this design rainfall. In general, SCS uses a 24-hour rainfall, and they will tell you what that cumulative rainfall is for your area. And before this, by the way, you have to also select what rainfall frequency that you're going to be using. I don't know if I did that or not in my example. Let me go back here. I don't think I specified the return period for this design storm, and therefore keep that factor in mind that this calculation of P depends on that too. Um, that's what I made a note here, that the typical SCS method uses a 24-hour type 2 rainfall. That's for the most of the U.S. It's called type 2. For east and west coastal areas of the United States, there are two other types, type 1, 1A and 1B for West Coast, and type 3 for the Gulf area. So please refer to the SCS methodology book for that. They have tables there showing all the design rainfall amounts for different return periods. The duration is fixed, 24 hours. Anyway, once you get past that step, we calculate using the curve number we just got of 83.6. We'll calculate these parameters. One is the sorptivity, the other is the initial abstraction, and from that, using this formula, I calculate the capital Q, which is equal to total rainfall, P minus IA squared divided by P minus IA plus S. So that's what I've done here to calculate a volume of direct runoff of 1.13 inches. Now remember, I can convert this into cubic feet or whatever I choose to in any other unit. In this case, I just asked you what the volume represents in cubic feet. That's just to show you how to convert a depth to a volume. Obviously, areas will be involved in that computation. In this case, since I'm going into cubic feet, 0.05 square miles times 640 times 43,560 converts into square feet of area. And multiply that with the depth in inches, you get in cubic feet. Okay? Now, please work on this problem. In this case, I intentionally changed what I set it up is a typical application of this method in urban areas. For example, here you have a 1,000 acre catchment that we're going to develop. Initially, it's in pasture in good condition, and its curve number is 74. That's what we call pre-development conditions. And then we're going to do a post-development, urban development of this area, which will be composed of this following land use breakdown, 1, 2, and 3. So what I'm going to ask you to do in this problem is to get the overall composite number and a few other questions to answer from that. And please work on this. It's a very good, I think, problem to work on to fully understand. Now, keep in mind, up to this point in the SCS method, all we have done is calculated the volume of direct runoff in inches. That's all we have done. I will go next to show you how to compute the peak flow. Remember, the rational method gives you the peak flow, QP. And that's what we really need to size a pipe to handle this runoff. The peak is the most critical parameter. Let me scroll down, see if there are any other questions up to this point. Um, what is the definition of sorptivity? Somebody asked me that question in the SCS method. That's a good question. That's probably, I tell you honestly, that's the most evasive parameter in this method. But it kind of represents the maximum soil can absorb, the maximum amount of water a soil can absorb. And that's one of the major criticism of this method comes from that parameter because it is connected to the curve number, and it's very hard to give a physical interpretation of that parameter. Other than basically that's what I just told you. Is this for a 12-hour period? Now, what is 12-hour period? Now, that's a good one. Are you talking about the rain? Which problem number? Somebody's asking me about. You figured it out. Okay. I'm glad you figured it out. All right. Let's move on. There are no other questions. Um, please work on that problem number 4 there, and we'll now pick up how to compute the peak flow. Remember, I just told you that the most important thing is to calculate the peak discharge computation. The formula that the SCST-55 uses is given right here on this slide. It's a very simple formula. It's not that complicated to use. It has basically 4 variables on the right-hand side. This is QP and CFS. Remember, the SCS method uses units in the U.S. system of units. So please stick to that. If a problem is given as SI, convert them. I strongly recommend you do that. For example, this QU, which is called the unit peak discharge, is obtained from a graph. I'll share that graph with you in a minute. And the units of that are in CFS per square mile per inch. And that's why it's called a unit discharge, unit peak discharge. It's like a unit hydrograph peak, but I won't get into that discussion at the moment. All I'm going to say is what it basically where it comes from and what it represents. You have to multiply by area. This area, by the way, is not in acres but in square miles. Keep that in mind. So this is the watershed size in square miles. You're going to multiply by that, and then the direct runoff volume, or what they call rainfall excess here, Q, capital Q in inches. And finally, this pond factor F. This might confuse you a little bit, but they have a factor to recognize the effects of storage, natural storage in the watershed. And typically, if it's not given, assume it's 1. That means 1 basically means you're neglecting that storage. What they're thinking is that if there is a lot of natural storage, such as natural depressions or some kind of lakes in your catchment, they do hold back the water, and therefore they can cause some attenuation in the peak flow of runoff. It's like providing natural storage. It's similar to a detention basin storage concept that we use a lot of times detention basins to reduce the peak flow coming out of the catchment. So it's kind of the same effect, and therefore F, if it's 0.75, for example, that means basically 25% reduction in the peak. So you'll use 0.75 times the QP here. All right, so having said that, let's move on to see how to get all these. The first one is the most challenging one, is the time of concentration. The reason you need the TC is to use that figure that I'm going to show you to calculate that peak flow, QU, you need the time of concentration. It's driven by this variable. SCS has 3 components. Now, on the exam, they might just give you 1 or 2 of the components, or they might give you the TC altogether. If they do, that's fine. Use it directly. So you don't have to go through this whole process that I'm going to go through with you in order to, on one particular problem. It may not happen. On the other hand, there are some worksheets in that TR55 manual that you might want to take with you that make this computation a lot easier. They have basically, the concept is very simple. They have two overland flow components. If the overland flow is less than 300 feet, they call it sheet flow, and if it's greater than that, they call it shallow concentrated flow. And both these 1 and 2 are basically overland flow times. So if the overland flow distance is greater than 300 feet, neglect the number 1. Just go straight to number 2. And I'll show you how to calculate this particular travel time. Finally, the channel or pipe, if there is involved, if there's a segment involved, calculate the travel time in either of these segments. This is typically done through Manning's formula. That's the point where I'm going to show you that Manning's formula that I did not show you at the rational method when we discussed the rational method. Basically, that's when you use that equation. So let's go through an example here, but before I do that, here are some of the equations that you'll see in TR55 manual. This is for basically number 1, that's for computing the sheet flow. Remember, this is for overland flow less than 300 feet. It's an empirical formula, so respect all the units. It's in US units and SI units. And this P2 right here is a 2-year rainfall. By the way, that's a 2-year right here. It's a 2-year 24-hour rainfall depth in inches. You can obtain this from TR55 manual, or they'll probably give it to you in the problem also. So look out for that because it requires that. The only other thing it needs is this N. This is not the typical Manning's N that you see in concrete pipes or something. It is basically the overland flow roughness, trying to capture that. And L is, of course, the length of the overland flow distance in feet. This time, by the way, comes out in hours. The N value that I just mentioned to you a minute ago comes from this table. You notice here the Manning's N coefficient is much, much higher than for typical pipes. For example, around here we have what is called Bermuda grass, and the N value, Manning's N or roughness coefficient, is 0.43 for that surface. And this is basically like a retardance coefficient. It slows down the runoff. It increases travel times, which is the primary goal for reducing peak flows generally. So therefore, overland flow, the rougher the surface, the better it is basically from a development point of view. So keep that in mind. The next thing you'll do is for computing the shallow concentrated flow. This is the next component of overland flow. This is for overland flow greater than 300 feet. They recommend using this figure. It's fairly straightforward. They will give you the slope of the overland flow surface. That's what you'll need. Using that slope, in this case it's in feet per feet, go across, and I'm doing an example here. For instance, if it's a 15% slope, the value is 0.15, we have to divide by 100. And for that slope, you can if it's paved or unpaved, depending on the type of surface, overland flow surface, you can swing and get the velocity, use this curve to get the velocity of the overland flow. In my example, that velocity is 6 feet per second, and using the velocity, you can determine the travel time as length divided by the velocity. Now remember, when you do this mathematically, the computation, length, say, typically is in feet, and the velocity is in feet per second, the answer travel time will come out in seconds. Then you might have to convert into hours or minutes, whatever unit you want to convert to. So this is the figure they used, or they recommend you use for overland flow, the second component. Finally, for the third component, if they give you a channel or a pipe in the along that flow path, the maximum flow path, then we use the Manning's formula. I've basically specified the Manning's formula here for you, for those who have not seen this equation before. They usually specify this in terms of velocity. This is in US units. There's a coefficient 1.49 here, while as there's no coefficient. For SI, it's 1.0. But N is called the Manning's roughness coefficient. Now, this is not the same N that I showed you for overland flow, although the concept is the same. But this can be obtained from tables. I'll show you a table here in a moment. For example, for a concrete pipe, typically that N value, Manning's N, is about 0.015. R is the hydraulic radius. This is probably by far the toughest thing to get in this equation. It's defined as the flow area to the wetted perimeter. All I can say is if for a full pipe flow, like in this note I show here, for a full pipe flow, D is equal to 1/4 the pipe diameter. That's the only time we have a physical interpretation of that parameter. So if your storm sewer system is surcharged, if you can assume that, then you're okay. But that's not always the case. I would say they'll give you these hydraulic radius. And one special case is an open channel system. We often call it a wide rectangular channel. In that case, the hydraulic radius can be assumed to be equal to the flow depth. Okay, I will show you those two special cases in my example. S naught is the slope. This is the longitudinal slope of the pipe or the channel. It's an average slope. That's based upon, in pipe systems, on the invert elevations of the manholes. One upstream, one downstream. Obviously, the flow has to go from higher elevation to lower elevation. That's what we call a sustaining slope. Now, here's a small example I've set up. Obviously, please don't be taken aback by this example. I just set it up to show you how these various components are computed. On the exam, they might just give you one of these components, or maybe a combination of two at most, but you should know how it all works in terms of computation-wise. And that's the reason I picked this particular example. I have four major paths here. Basically a sheet flow component, overland flow sheet flow, less than 100 feet, less than 300 feet. And then I have an overland flow concentrated flow component, 300 feet. And finally a pipe and open channel. I've given you all the slope information in this column for each of these components. And for the pipe flow, it's a 24-inch pipe. Manning's N is given. We're going to assume full pipe flow condition for the pipe. But for the open channel segment, I've given you the flow depth in this example. But as I said, that's usually where you may run into a problem. Of course, you always need the hydraulic radius. So somehow you need to relate the hydraulic radius to this. In my case, I'm going to assume what is called a wide rectangular channel. I know how many of you heard of that. That's a channel where the flow depth and the bottom width is very wide. That means approximately 20 times greater than the flow depth. If it meets that requirement, one of the assumptions we can make is the hydraulic radius is equal to the flow depth. That really solves a lot of our headaches when you apply the Manning's formula for an open channel system. So you can calculate the velocity very quickly by using the flow depth directly. In my example, I'll do that. I'm going to do the overland sheet flow component. Just use the empirical formula. And I have to go a little bit faster here because of the time part of it. So I'm going to go through this example quickly. If you have any questions, you can always email me. Somebody asked me, what is S naught? S naught is the slope of either the pipe segment or the channel segment of the overland flow surface, the surface slope. A slope is in feet per feet or specified as a percentage, okay? This essentially is the longitudinal slope of any of those components. In this example, I'll show you again what that slope, where it comes into play. So in this case, the first component is overland sheet flow. It is Bermuda grass. I've given you the n value, and here's the overland surface slope of 0.05, and that plugs right into this formula. There's the slope term right here. It's obviously travel time is be inversely related to slope, because the milder the slope, the water is going to be held back. It won't travel as fast. And so in this case, that's the first travel time. This is the second one. This is for the shallow overland concentrated flow. I've given you the slope here as 0.015. So if we go back to that figure, this one right here, 0.015 slope, it puts me right in this, right around here. So it's unpaved. So I go across to the unpaved curve labeled unpaved. And if you swing down from there to this point right here, it'll be about 1.8 feet per second. So please go ahead and verify that for yourself. And in my case, I've already shown that here, that the velocity from that graph will be 1.8 feet per second. Length divided by velocity gives me the travel time. Just be careful with units again. The length is 300 feet divided by 1.8 will give you basically 0.046 hours. Finally, the path, those two paths, the pipe flow and the open channel flow computation involves the Manning's formula. So the main thing is, I'll skip all the other steps right now. Those are just all the variables you'll need, all the quantities you'll need to apply the Manning's formula to calculate the velocity. It obviously uses the Manning's n here, 1.49 over n. And then, of course, the r to the power 2/3, that's the hydraulic radius. For a full pipe flow, as I said, it's equal to the radius of the pipe. And then the slope, 0.01, that's the slope of the pipe for the person who asked me about what slope is. That is based on elevation differences between the two manholes, the entrance point and the exit point. And in this case, it comes out to be 6.26 feet per second. Typical velocities in pipes should be between 6 and 9. And finally, the travel time, in this case, the length divided by velocity. You always do this computation, by the way, in the SCS method, is the length divided by the velocity. Finally, for the open channel segment, you do the same thing, except the hydraulic radius I'm going to assume here, R is equal to Y. That's for a wide rectangle channel. And then I can compute the velocity thereafter. So anyway, the final travel time is the watershed concentration, or time of concentration of the watershed is the sum of all these travel times. And in this case, if you add up all the 4 travel times, it's 35.28. Now I know some of you might say, will I get the entire problem like this on an exam? Probably not. You might get a component of it, or they might give you in all these total travel time here of 35.28 minutes. That's the time of concentration. But I can assure you that if you're doing the rational method, for example, they will definitely involve a pipe segment, travel time in a pipe, because you have to determine that when you after you select a pipe size between two manholes. Remember I mentioned in order to go further downstream in the design point, you have to know the travel time in the pipe. This is how you do it, even in that method. You use the Manning's formula to calculate travel time by using L times the velocity, okay? So either methods you will need to do this type of computation. In general, they can give you a separate problem, for instance. What's the travel time in this pipe? In that case, they may give you a discharge, okay, in the pipe size. So you have to calculate the velocity from that directly. Remember Q divided by A, the flow area. It gives you the velocity directly. And then if they give you the Manning's formula with all the information, you can compute it from that also. So velocity in open channel systems, you should be able to do that same type of calculation, except use the flow depth instead of the pipe size. All right, moving on. I've set up a problem here for you, by the way. Please work this out, problem number 5. It's on the SCS method. Now finally, the peak discharge. Now we're all going to put all this together now. Now that I showed you how to compute the volume of rainfall excess using the SCS method, that's capital Q. How to calculate the time of concentration. Now, and also how to do all the runoff computation, curve number computation. Now, in general, for peak discharge, this is the last step. You will need to compute a composite curve number. These are the steps you'll go through. You'll always compute the sorptivity S in the initial abstraction. That's for the runoff computation purposes. But you also will calculate this thing called IA or P ratio, and I'll show you where to use that in a minute. Finally, number 3, you'll still compute the runoff volume Q, and then based on that information and the time of concentration, you'll get the unit peak discharge from a figure I'll just show you in a minute. And of course, the pond factor, if it's not given, just use 1. Don't worry about it. And finally, you compute the peak discharge. So these are all the steps, sequential steps one has to go through in order to get the peak discharge from using the SCS method. Now, somebody has a question here. Let me see what that is. IA is 0.2S unless specified otherwise. Absolutely right. I'm glad you brought that up. In the SCS method, the initial abstraction is 0.2S by default, but it is generally recommended in urban areas to go with 0.1S. So you might have to change that depending on what they ask you to do, okay? All right, moving on. Here's the graph for the peak discharge computation in the SCS. Here it's a function of time of concentration. That's what you have to know to use this. By the way, this is called type 2. There are curves for other three types, one for mainly for the coastal regions. This is generally used for most of the U.S. It covers a major portion of the country. It uses obviously, is basically I've mentioned here in the title itself, there are 1A, 1B, and type 3 curves, which you can get from the SCS manual if you need to. 1A and 1B are for the western coast United States, mainly California and Washington, that areas. And type 3 is the Gulf states, Louisiana and so on. So Florida, because these are affected by hurricane activity, and therefore they separated them out. But anyway, to use this curve, you need the time of concentration of that flow path or the watershed. And by the way, in the appendix, I've included some other formulas. If I have time, I'll show it to you, where you can use, which formulas you can use to calculate this TC for natural catchments as well, instead of going through the entire computation as SCS does. So the SCS methodology that I just outlined a few minutes ago is good for urban areas type of settings, but for natural catchments, there are some empirical formulas also you can use directly that give you the TC. So given that, you can calculate the unit peak discharge from this graph. It's based on this IAOP ratio. In my example, if the IAOP ratio is greater than 0.1, use the top curve. If it's less than 0.5, use the bottommost curve. In between, you can extrapolate. I'll show you the example that I've set up for you, how this will all work out. In this case, I'm giving you the TC, and this will be a typical problem on the exam. 250-acre watershed, 25-year, return period is 25 years. It's still a 24-hour design rainfall, type 2, and I've given you the value of the rainfall amount here, 6 inches. I also gave you the composite curve number, so that saves you some problem. Hopefully they will not link problems A, B, and C like that. If you make a mistake in one, you'll carry that mistake over to the second. So hopefully these are independent specifications in the problems on the exam. And then neglect storage in lakes and ponds, that means pond factor is 1. And so let's look at the computation quickly. I've done the usual steps. We've gone through this several times here in our discussion today. The sorptivity S, which I told you is the maximum amount of rainfall a soil can absorb, is their interpretation of it. It may not be mine, but anyway, that's 1,000 over curve number minus 10. I mean, there's obviously a lot of disagreement on that because infiltration can keep proceeding even if it's raining. But of course, if you cut off after 24 hours, here in this case, you're getting 6 inches total rainfall. So this is about half of it is what it says the soil can absorb maximum. All right. I don't know whether you agree with that or not, but anyway, IA is 0.2S, 20% of that. And IAOP ratio, this is the new one. In this case, 0.11. That's below that 0.10 curve that I just showed you earlier, so we're okay there. And finally, you'll need this runoff volume in inches and the unit peak discharge. This is from slide 58. And finally, I'll put it all together. In this case, that unit peak discharge, I'll go back to that slide for a minute to show you. Keep in mind the time of concentration and IAOP ratio. These are the two you'll need in order to get that IU from that figure. The time of concentration is 1.5 hours. So I'm going back to that figure briefly. The time of concentration is 1.5 hours. IOP ratio is close to point this curve. The swing over, the one shown here in my black dashed lines, is about 285 CFS right there. Okay. So that is, by the way, CFS per inch per square miles. So therefore, if you multiply by the area, etc., you should get the peak flow in CFS. All right. Up to this point, I've reviewed basically the rational method and the SCS method of both these methods. Let me answer this, see if I can take this question. What is IA? Again, somebody else raised the same question. I think I answered this once before. Another gentleman raised the issue. That's initial abstraction. That basically looks at is the way SCS method handles. If you remember, I said initial losses. That is when it rains, you lose some of the rainfall to interception and depression storage. That's called initial. You lose all that initially during the beginning of a storm before infiltration kicks in, and that's called the initial abstraction. The SCS method of doing that is through the parameter IA. Okay. All right. That's what initial abstraction means. It's initial losses. Typically about, I would say, if they don't give it to you in the rational method, we use like, for instance, they typically, you can use 20%, 10% of the storm as initial loss. You just abstract it from rainfall and continue with your design. If you want to neglect it, that's fine. But in the SCS method, you have to kind of incorporate it into the rainfall analysis. Okay, so let's finally review a little bit unit diagram since we have a few minutes. I only included this upon the request of some participants in the past. I was told, I'm not sure about this, but sometimes they do ask what a unit diagram is or simple use of it, and that's what I will do here. First, let's look at the definition of a unit diagram. That's probably the most confusing thing for a lot of people. You have to remember a couple of things in order to understand this. First of all, a unit hydrograph is a direct runoff hydrograph. That's the first thing. That means it does not involve any base flow, groundwater stuff, etc. It's a direct runoff hydrograph. Remember I showed you how to calculate the volume under a direct runoff hydrograph in a previous example. I call it DRH, okay, direct runoff hydrograph. It is it is associated with the watershed due to 1 inch of rainfall or 1 centimeter. Please do not do unit conversions here. If they give it to you in SI units, work the problem in SI. If it's given in US units, work it out in US. Stick to that. Typically, they'll give you the rainfall in inches or centimeters. And of course, this is rainfall excess, by the way, because that's what a unit hydrograph is. It's a direct runoff hydrograph due to 1 inch of rainfall excess generated uniformly across the watershed in an effective duration called TR. That TR, by the way, is called the unit hydrograph duration. For example, in my graphics here, this is a 2-hour unit hydrograph because the effective duration, the rainfall excess, is defined every 2 hours at a constant rate of 1.2 centimeters per hour, so which produces 1 centimeter of rainfall excess. In this case, it's a 50 square mile, kilometer square watershed. So essentially, this is a hypothetical definition. This is what they're saying. If 1 inch fell or 1 centimeter fell over this entire watershed uniformly, which is highly unlikely to happen if you have a large watershed. So that's a unit hydrograph also has its problems when you extend this method to large catchments. But anyway, that's what it produces. You have to accept the shape. And of course, deriving this, I'm not going to get into that in this discussion, but they can be derived. They have to be derived from rainfall runoff data, or synthetically, they can also be derived. Either case, this is what is going to be given to you. Okay. Now, there are some principles that we use in order to use it. One is called linearity, lagging, and so on. Linearity means if the unit hydrograph is due to 1 centimeter or 1 inch, if 2 inches of rainfall excess occurs in the same duration, then you double the ordinates. Okay. Lagging means if, say, 1 inch fell in the first TR minutes or TR hours, remember the effective duration of the unit hydrograph can be anything, and that has to match up. The rainfall excess duration must match up with that. And then it have, say, another amount produced in the next TR hours, then you can add the effects of these two rainfall excess amounts. So those are called lagging, and then finally you can add these effects That's called the superposition. I'll illustrate these principles through an example, okay? You can also use these convolution formulas for some people like this. I've taken the liberty to duplicate them for you here. For example, these equations will give you the direct runoff hydrograph based upon rainfall excess amounts. Those I call the P's, capital P's, P1, P2, P3, etc. And the U's are the unit hydrograph ordinates. So essentially, the P's, by the way, are the rainfall excess depth in inches. The key thing you have to make note of is the time interval for the for the rainfall excess amounts must match with the unit hydrograph duration. What that means is if the unit hydrograph is a 1-hour unit hydrograph, these rainfall pulses that you see here must be specified every 1 hour. These unit hydrograph ordinates are normally taken the same time interval, but they don't have to be. These are instantaneous discharge hydrograph ordinates from the unit hydrograph. So anyway, this is how you use them. This is called a convolution process. To get the first flow, you take P1U1. To get the second flow, you take P2U1 and then plus P1U2, etc. So in this case, the subscript of P1 decreases over as you go along, and the subscript of the unit diagram increases in the process. These are called convolution equations. You don't have to use these. I'll suggest you use a tabular method. I'll show you in a minute, which is a lot easier to use. But in general, this equation is important. This shows the relationship between the number of direct runoff hydrographs you're going to get when you do this convolution process based upon the number of rainfall excess amounts they give you, called M, and J is the number of unit hydrograph ordinates you're going to be using. So N plus J minus 1 should be equal to N. It kind of tells you in advance how many of these Qs to expect from the number of rainfall excess amounts and the unit hydrograph ordinates. I will get back to that when I do the example in a minute here. So let's look at this small example. It's a half-hour unit hydrograph I'm going to specify. And I'm also going to give you the rainfall excess depth. Most likely that's what they'll do on the exam. Remember, the one way to get this rainfall excess depth was to use that fee index. That gave some of you some headaches when I went over that method. But in general, if they give you the rainfall excess, that's fine. So in this case, 2 inches in the first half hour, 3 followed by 3 and 1. And then, of course, I gave you the base flow just to show you how to come back with the total hydrograph, but don't have to worry about that in this example because the emphasis is on the direct runoff hydrograph. For the stream flow hydrograph, which I'm also asking here, you basically have to add the base flow back again. There is a question here before I show this example. For TC of 1.5 hours, is Q 300? Well, somebody reads it as 300. I think if you read it carefully, it probably should come to 285, okay? This is in the SCS peak, unit peak discharge method. Somebody had a question. But go back to that, and if you find some time, print it out and read exactly. You'll come closer to 285 than 300. But you'll be off a little bit, doesn't really matter. In the multiple choice, you'll pick the closest Q peak that you get. They specify. All right. So to get the direct runoff hydrograph using the unit hydrograph methodology, here's what I would do. I would set up a table like this, a simple table. It looks a little messy, but it's very quick to do once you set it up. In the first column is the time period. Remember, every half an hour. So 1 to 2 is half an hour time interval. The rainfall excess was already given to me, 2 and 3 and 1 inch. Obviously, that happens in the beginning of the rainfall event or the rainfall runoff event. Uh, we'll use those excess amounts to do the convolution in a minute here. So here on top here, write down all the unit hydrograph ordinates. In this case, it starts from period 1 to period 9. So there are 9 unit hydrograph ordinates. That's capital J. M is 3 right here. And use the number of unit hydrograph ordinates called J is 9. So if you take that formula that I told you about M plus J minus 1, you can expect basically N equal to 11. That's 11 ordinates of the direct runoff hydrograph. And that's what you will see when I'm done with this convolution process. You will get 11 hydrograph ordinates. Now in this case, what you do is you put the unit hydrograph on top. Now, by the way, in the exam, they won't give you this many unit hydrograph ordinates. They might give you maybe 2 or 3. And the rainfall X's also, they might give you 1 or 2, just to see if you understood the process. Set up the unit hydrograph on top, and here you, in the first column, you multiply the first unit hydrograph with each of these rainfall X's pulses. So 2 times 404 is 808, 3 times 404 is 1212, and so on. Then do the same thing with the second unit hydrograph ordinate, but this time you lag it by half an hour because it comes half an hour later in time period 2. So that's 2158 is 2 times 1079. 3 times 1079 is 3237, and so on and so forth. Notice 1 times the unit hydrograph ordinates is the unit hydrograph ordinate itself, because 1 inch of rainfall excess should produce the same hydrograph. And do the same thing, go on doing for all the unit hydrograph ordinates each time you lag it, like I've done in this table, and then add them finally across, and that will be your total direct runoff hydrograph when you sum them up. Now keep in mind, here I've shown you the total. I want you to go home and check to make sure you did your computations correctly. What you do is you simply, remember I showed you an example earlier, how to compute the volume under direct runoff hydrograph by summing all these ordinates, multiplying by delta T. In this case, delta T is half an hour, you'll get CFS. So if I took this and multiplied by half an hour, zero point 0.5 hours, I'll get this volume in CFS hours, which you can convert to cubic feet, and then divide by the drainage area in square feet, you'll get the volume of runoff in feet, which you can convert to inches. Obviously, that should match up with the rainfall excess amount. In this case, it was 3 plus 2 plus 1. This is 6 inches. So you should see that conversion give you 6 inches of rainfall volume of direct runoff. If it doesn't, means you goofed up somewhere. So that's one way to run a quick check. I've set a small problem for you in this case. I've had some participants in the past email me questions about this part D because I intentionally did not give you the drainage area for this problem. That's because you can determine this independently. If somebody gave me a unit hydrograph like I've done here, you can take the volume under that unit hydrograph, which by summing these ordinates, you must recognize that that's equal to 1 inch, and therefore use that condition to calculate the drainage area, watershed size, and D. Or you can alternatively use the volume of direct runoff in part C, which you would have computed after you get the direct runoff in B, and use that volume to calculate essentially the drainage area. Both should give you the same answer. Okay, so that's a little trick question. You might see that on a problem. They might even give you direct runoff volume. They'll say, here's the volume of direct runoff under a unit diagram. If they do that, you must immediately realize that volume probably is given in cubic feet or something like that, or in CFS hours. Then you should be able to, from given the duration of the unit diagram or the time frame they'll give you, you should be able to convert that to inches. Okay? And finally, good luck on the exam. I've included some additional topics for you in the appendices. I just want to show you a few things before we quit here. Here are some references that are included that you could see if you can take with you. By the way, here are the answers to all my problems that I've set up in the session. You can try them, and if you're still having trouble, please email me. I'll be happy to help you out. Some additional things I wanted to go over was, one, this particular table. This is the one that I told you about how to select the return period based upon the system you're trying to design. This is a very difficult table to find anymore, because the newer textbooks are kind of eliminating it. But I think one of the sources you can always refer to is called the DAMS 2 book. They probably should have it. But the older hydrology textbooks do incorporate this. For example, if you're doing an urban drainage system, storm sewers in large cities, they recommend a 25 to 50 year return period. Airfields, high traffic, 50 to 100 year. So please use this table as a guide to select the return period if they don't specify that, that is. And of course, I've included here 100-year 6-hour rainfall duration curves instead of the 24-hour, just to show you what they look like if you want to do a different storm duration. Uh, I've also included some information on the methods, other methods to compute time of concentration. If you remember, I mentioned that particularly you pay attention to this Kirpich formula that's very, very popular in the U.S. It's an empirical-based formula, so please respect the units. It requires only the length of the channel, or basically that's the total length along which you're computing the travel time or the time of concentration, and S is the average watershed slope. So this is a formula that can be used for natural catchments to get TC. For urban areas, they recommend some adjustment to it. So please read the remarks section here to make sure they're applicable. The federal highway, if you're doing an airport type of design problem, they recommend using their formula, FAA. And finally, of course, the last, I would not use this lag equation. I think they pretty much dropped it. The others are all basically more analytical form. They're mainly for overland flow computation purposes. The main one, of course, we reviewed is here in this our discussion is the CS average velocity. I kind of like this because they leave it open. They define their TC as sum of all travel times. Don't let that 60 throw you off there. That's just to convert the answer to minutes because length will be in feet and velocity in feet per second. The answer usually comes out in seconds. In order to conform to the T in minutes in this table, remember the T comes out in minutes, they go and divide that by 60. It's a unit conversion thing. All right, thanks for listening, and I hope I've covered some aspects of this subject, and it's very difficult to cover everything in 2 hours, but definitely this is a topic that you might want to review. I doubt if this will come in the morning session, but if it comes in the afternoon for those who are planning to take this as the thing, I'll also review some of this later in a depth session, but I suggest you look at this too. Thank you, and have a good day, and I will talk to you all again, at least in the depth sessions, for those who are